When we build things, we generally expect the environment to just, well, get out of the way. Like we pour concrete, we erect steel, and the world is supposed to respect those boundaries.
Right, yeah. We really love to impose human geometry on a chaotic world.
Yeah.
Solid walls, straight lines.
It gives us this false sense of control over our surroundings.
Oh, absolutely. But then you introduce fluids into the mix. You
Yeah.
put that rigid wall in a rushing river, or, I don't know, fly it through the sky at hundreds of miles an hour.
And suddenly that rigid boundary isn't a wall anymore. It's an obstacle. It creates this violent, chaotic turbulence.
Yeah, exactly. The fluid always fights back. And usually the fluid wins.
Okay, let's unpack this, because today in this deep dive, we are looking at the explosive collision of additive manufacturing, which you probably just know as 3D printing, with the incredibly unpredictable, harsh world of fluid dynamics and marine environments.
Yeah, we've got a fantastic stack of sources today.
We do. We're looking at peer-reviewed studies from Extrica, Applied Sciences, and Purdue University, plus an economic readiness report for the island of Guam, and the specs for a wild, futuristic Texas project called Ocean Grid.
It's a lot, but it all connects perfectly.
Right. So our mission for this deep dive is to explore how 3D printing is breaking out of those clean, climate-controlled labs and stepping into the harshest environments on Earth. We're talking about silencing aircraft landing gear, fixing broken supply chains on remote islands, and even building massive robotic desalination batteries right in the ocean.
It's wild. But, to understand how we can eventually print entire structures underwater, we actually have to start with how 3D printed shapes interact with fluids in motion.
Okay, lay it on us.
So there's this fascinating study from Extrica. They looked at a specific aerodynamic nightmare, which is fluid hitting cylindrical shapes.
Like an aircraft landing gear hanging down in the wind.
Exactly. Or water rushing past a cylindrical bridge pillar. They looked at a flow state with a Reynolds number of 60,000.
Okay, Reynolds number. That's basically a turbulence rating, right?
Yeah, pretty much. It means the flow is highly unstable. When a fluid hits a solid cylinder at that speed, it creates a turbulent vortex street.
A vortex state. Sounds intense.
It is. It's a chaotic, vibrating wake that causes immense noise and structural stress. And historically, engineers just, accepted that vibration as a cost of doing business.
But these researchers didn't.
Right. They decided to wrap the cylinder in a 3D printed porous coating. They used MSLA 3D printers, which use UV light to cure liquid resin to get extreme precision.
We're talking layers just 22 to 29 micrometers thin, right?
It's incredibly thin.
Yeah.
But they weren't just printing random foam. They tested highly specific mathematical lattice geometries, specifically cubic, diamond cubic, and Kelvin cell lattices.
Okay, let's visualize those for you listening. A cubic lattice is like a perfectly stacked grid of scaffolding. But a Kelvin cell, that's a much more complex shape, right? Almost like a 14-sided polygon.
Spot on. Yeah, like a truncated octahedron packed together to mimic dense foam. And the diamond cubic is equally complex. It mimics the tetrahedral bonding of carbon atoms in a diamond.
Wow. So I guess the assumption was that any of these porous sponges would soften the impact of the fluid?
That was the initial thought, yeah. But the results proved otherwise. The diamond cubic and Kelvin cell structures had incredibly high airflow resistivity.
Meaning the fluid couldn't actually pass through them easily.
Exactly. They were too dense, so they just acted like solid, rigid walls anyway.
No.
The water or air crashed into them, got rejected, and created the exact same chaotic vortices.
Oh, man. So wait, why does the specific shape matter so much? I mean, isn't a hole just a hole?
Well, what's fascinating here is how the internal geometry entirely redefines how the physical object exists within a fluid space.
Okay.
The cubic lattice vastly outperformed the others. It has a much simpler structure with a massive amount of open area on the outermost layer.
Oh, I see.
Yeah, so when they printed a thick cubic coating at 95% porosity,
Right.
it allowed the fluid to actually enter the structure.
So instead of water hitting a brick wall and swirling violently, it's kind of like a microscopic pinball machine.
I love that analogy, yes.
The fluid rushes into those tiny printed channels, and as it violently bounces around the internal scaffolding, it exhausts all its kinetic energy.
It dissipates its thermal and viscous energy
Oh, yeah.
internally, yeah. By the time it trickles out the other side, the flow is completely calm. That thick 95% porosity cubic coating reduced peak turbulence by an astonishing 74%.
Oh, wow. That is a massive drop.
It fundamentally altered the aerodynamic and hydrodynamic reality of the object.
Wait, I have to challenge the physics on this, though.
Go for it.
If the cubic structure is 95% empty space, How does it survive the physical impact of a fluid slamming into it at a 60,000 Reynolds number? Shouldn't a fragile 3D printed resin lattice just shatter instantly?
It seems totally counterintuitive, right?
Yeah.
But the fragility is actually protected by the porosity.
Really?
Yeah.
Because the fluid doesn't slam into a solid surface, it penetrates the structure. So the pressure is distributed evenly throughout the entire internal volume, rather than being focused on a single external impact point.
Ah, so it absorbs and disperses the force rather than resisting it.
Exactly. By controlling the microscopic geometry, we can make a physical object sort of softer to the fluid around it.
That is wild. And if we can master fluid dynamics with these prints, it makes me wonder, why stop at printing objects to place into the water? Like, why not take the printer itself underwater?
Well, that is a massive leap in complexity.
I bet.
Yeah, we have a study from Purdue University that outlines the absolute nightmare of underwater concrete printing.
Yeah, extruding concrete underwater sounds terrible.
It introduces two massive hurdles, buoyancy and washout.
Buoyancy I get. The water's upward force essentially reduces the density and weight of the concrete, so it wants to float instead of settling down.
Right. And washout is when the surrounding water literally strips the cement paste away from the heavier aggregates, like the sand and rocks, as it comes out of the nozzle.
So you just get this cloudy, useless mess.
Yeah, the layer you print completely loses its structural integrity. It has zero buildability.
Meaning the first layer can't even hold up the weight of the second layer.
Exactly. The whole print just collapses into a pile of sludge.
But the Purdue researchers solved this, right, with a two-stage chemical intervention.
They did. It's pretty brilliant. Traditional concrete printing involves mixing all your chemicals in a batch before pumping it. But Purdue used an ADB robotic arm equipped with a dynamic mixing nozzle.
Okay, so they're mixing it right at the end.
Yes. They inject an accelerator aluminum sulfate right at the print head, literally milliseconds before the concrete touches the water.
Wow. And they had to crank the dosage significantly for that to work underwater.
They did. In open air, they use 18 milliliters per liter of this accelerator. Underwater, they doubled it to 36 milliliters per liter.
I'm guessing the aluminum sulfate triggers a really rapid chemical reaction.
It promotes incredibly fast hydration of the cement particles.
Right.
It causes the concrete to undergo rapid flocculation.
Flocculation.
The particles instantly clump together and stiffen the exact moment they leave the nozzle. It gives the extrusion instant green strength, which completely resists the washout effect.
That's incredible. And they actually managed to print U-shaped and hollow prismatic structures completely submerged, right?
They did. They even tested overhangs. Printing out at a 0-degree angle and a 15-degree angle worked perfectly.
No way. And the compressive strength matched concrete printed in the open air.
It did is a major breakthrough for underwater infrastructure.
Yeah.
But, there are still limits.
Right, the 30-degree overhang.
Yeah, when they tried pushing the overhang to a 30-degree angle underwater, the print failed. Gravity and buoyancy eventually win.
Well, okay, concrete makes logical sense because it cures chemically, but the applied sciences source mentions printing titanium underwater, specifically Ti-6Al4V alloy for repairing marine equipment.
Yes, that is a whole different ballgame.
Seriously, how on earth do you fire an incredibly hot laser to melt metal in the ocean without it instantly cooling or boiling the water or just completely shorting out?
It relies on a process called laser metal deposition, or LMD, paired with a highly engineered drainage nozzle.
Okay, paint a picture for us.
So picture the print head moving along the surface of a broken metal propeller shaft underwater. The laser fires down the center, mounting titanium powder that's being fed into the beam.
But to prevent the water from instantly quenching the molten metal, I assume there's some kind of barrier.
Exactly. Surrounding the laser is a continuous high-pressure blast of shielding and drainage gas.
Oh, so it blows the water away.
Yes, this gas physically pushes the surrounding water away, creating a microscopic stable bubble of dry air right where the laser meets the metal. They call it a local dry cavity.
That is so cool. The laser is essentially operating inside a tiny moving diving bell at the bottom of the sea.
That's exactly what it is. The water never even touches the molten titanium until the print head moves on, and by then, the metal has already solidified.
Wow. It allows for metallurgical bonding completely shielded from the aquatic environment.
Right.
But, if you're listening to this, you're probably wondering why we'd go through all this immense effort to print a metal part in a bubble underwater instead of just, ordering a replacement part from a factory.
And that brings us to the logistical nightmare of the Indo-Pacific.
Yeah. We read this feasibility report from GA, the Guam Economic Development Authority. Guam is a tiny island in the Pacific, but it serves as a massive strategic hub for the U.S. Department of Defense.
Right. And because of its extreme isolation, if a Navy ship or an Air Force jet needs a spare part, say, a specialized high-pressure valve,
Hmm.
they can't just run to a hardware store.
No, it can take months for a ship to carry that valve across the Pacific Ocean. It's like being stranded on Mars. You don't want to wait for Earth to send a wrench. You want a Star Trek replicator to just print the wrench right there.
Point of need manufacturing. It is the holy grail of logistics. Waiting months for a part degrades operational readiness. You have multi-billion-dollar assets sitting idle, completely useless, because they're waiting on a piece of metal that costs a few $100s to manufacture.
But the GEDA report serves as a harsh reality check, doesn't it?
It really does. Industrial additive manufacturing is far more complicated than pressing print and walking away. Producing a part that is safe enough for a commercial jet or a nuclear submarine requires a rigorous 7-step industrial workflow.
Right. Step 1 is having the exact CAD software and technical data packages. Step 2 is path planning, simulating how the laser will move to avoid thermal warping. Step 3 is the actual printing process. But Step 4 is the real bottleneck.
Post-processing.
Yeah, you can't just pop a titanium submarine valve off a printer with a putty knife.
Definitely not. The thermal dynamics of 3D printing metal mean the part is literally welded to the metal build plate. To detach it, you need a wire EDM electrical discharge machining.
Which sounds intense. I'm imagining it's not a standard saw blade.
Oh, far more precise. A wire EDM uses a hair-thin wire electrified with thousands of sparks per second to literally vaporize a microscopic path through the solid titanium.
Vaporize. Wow.
Yeah, it cleanly slices the part off the plate through spark erosion without applying any mechanical force that could bend it.
But even after you slice it off, the metal isn't ready. Because 3D printed metal inherently has microscopic air pockets or voids inside it, right? Since it's built layer by layer.
Exactly.
And if you put a porous valve onto a submarine experiencing deep sea pressure, it's going to implode.
That internal porosity is exactly why Step 5 requires a furnace for hot isostatic pressing, or HIP.
Okay, what does that do?
The part is placed in a chamber flooded with argon gas and subjected to extreme heat and intense pressure simultaneously. This essentially squishes the metal from all sides.
It squishes the voids shut.
Exactly, crushing those microscopic voids shut and making the titanium fully dense.
And after baking it, you still have to run it through a CT scanner for non-destructive inspection. The Navy needs radiographic proof there are no internal microcracks before a mechanic will ever install it.
Right. So if we connect this to the bigger picture, Guam doesn't just need 3D printers dropped off on the dock.
No.
They need a massive, localized, high-tech industrial ecosystem. Technicians, post-processing ovens, metallurgists, inspection labs. Point-of-need manufacturing requires point-of-need infrastructure.
Right. Grom shows us how desperate the need is to eliminate shipping by manufacturing on-site, but they are bottlenecked by having to build that entire land-based infrastructure first.
Yes.
Which brings us to the craziest concept in today's deep dive. What if you didn't have to build the factory at all? What if the environment itself is the factory?
Ocean grid.
Yes, Ocean Grid. I was so excited to get to this.
This project takes in-situ or on-site manufacturing to its absolute extreme. Ocean Grid is a massive infrastructure initiative designed to solve 2 overlapping crises in Texas.
Severe water deficits and a highly unstable power grid. ERCOT, right.
Exactly. Normally, solving a water crisis means spending 5 to 10 years pouring concrete and building a massive desalination plant on the coast.
But Ocean Grid completely bypasses the land.
They do. They use robotic barges out in the Gulf of Mexico. These barges extrude a proprietary graphene-oxide ink directly into the seawater.
And the chemistry here is just stunning.
It really is. Graphene oxide, or grad ink, doesn't require a UV light or a chemical accelerator to harden like the other things we've discussed.
So what cures it?
The ocean's natural ionic strength, the salt already dissolved in the water acts as the catalyst.
Wow.
The moment the deg ink hits the seawater, the ions cause instant crosslinking. The polymer chains bind together rapidly in a process called gelation.
So the ink instantly turns into a self-supporting hydrogel lattice. The ocean literally serves as the factory floor.
Yes. And by doing this, they project they can build a 1 gigawatt infrastructure array in just 3 to 6 months.
3 to 6 months. But here's where it gets really interesting for you listening. Remember the Extrica study we started with? How geometry changes reality.
Right. These printed graphene lattices are designed with a specific geometry that allows them to operate in a dual mode. They tackle both the water and energy crises using the exact same physical structure.
Okay, let's break down the desalination mode first. Traditional reverse osmosis relies on brute mechanical force, right? Using massive energy-hungry pumps to shove seawater through tiny membrane filters.
It's incredibly loud, it's expensive, and it burns a ton of electricity.
But the ocean grid lattice ditches the pumps. It operates electrostatically. It applies a very low voltage, only about 1.2 volts, to the conductive graphene structure.
Because the lattice is printed with nanoscale pores, that tiny voltage acts like an electrostatic vacuum. It draws the sodium and chloride ions out of the water, trapping them inside the nanopores, while the fresh water flows freely through the larger, millimeter-sized printed channels.
That completely changes the economics of water. Without massive pumps, the energy requirement drops by 3 to 5 times.
It's massive. We're talking only 0.6 to 1.2 kilowatt hours per cubic meter of fresh water.
Which drops the cost to just 25 to 60 cents per cubic meter.
Exactly. And the second mode is grid power mode.
Right, because the underlying mechanism trapping ions on a high surface area graphene lattice using a voltage, that is exactly how a supercapacitor works.
Right. This giant water filter is simultaneously a massive battery.
That's wild.
The lattice doubles as a grid-scale supercapacitor, capable of storing 200 to 500 megawatt hours of electricity.
So when Texas wind turbines spin at night, producing excess cheap energy, Ocean Grid absorbs it.
Yes. And during a massive heat wave when the power grid is pushed to the brink of collapse, the graphene lattice can discharge that stored power back to the grid in seconds to stabilize it.
The sources refer to the financial model here as a triple stack of revenue. A 1 gigawatt array generates an estimated $300 million to $600 million annually because it's stacking 3 different income streams simultaneously.
Right, they sell fresh water, they sell frequency regulation services to stabilize the grid, and they perform energy arbitrage.
Which is buying wind power when it is cheap and selling it back when demand makes the price skyrocket.
Exactly. This triple stack means the capital payback on building the entire oceanic array is only 3 to 6 years.
The economics sound like a miracle, but we have to address the physical reality of the environment we are building in.
We do.
We are talking about extruding millions of gallons of graphene oxide directly into the Gulf of Mexico to build electrified, city-sized batteries. What is the biological cost to the marine life actually swimming through that infrastructure?
Well, the biological reality is mixed. Graphene oxide is a nanomaterial. Some studies show low toxic effects when autogo is used for water remediation. For instance, when tested on bivalves like clams, their behavior remained largely normal.
Yeah, but clams are pretty hardy, right?
Ugh.
The physical shape of graphene particles presents a severe mechanical danger to more delicate creatures, like fish. Gills are the primary entry point for oxygen, and they are incredibly fragile.
Right. Studies on early-stage salmonids like brown and rainbow trout revealed that while the chemical exposure didn't destabilize their heart rates, the microscopic physical structure of the graphene oxide particles acted like microscopic shrapnel.
Oh, that sounds awful.
It is. It caused severe mechanical damage to their branchial membranes. It essentially scratches and tears at their gills, causing irritation and necrosis, which is localized tissue death.
Wow. And it even disrupts their reproductive behavior, right?
Yeah, one study found that exposure to Jago caused an 11 to 23% reduction in nesting activity in fish. Introducing massive Jago structures into an ecosystem is not a biologically neutral act.
No, clearly not. However, the interception of 3D printing in marine biology does have a positive flip side.
It does. The Applied Sciences source highlights how researchers are using 3D printing to biomimic and assist marine life, rather than just imposing industrial infrastructure onto them.
Biomimicry is fascinating. Instead of just dumping old concrete blocks into the sea, scientists are 3D printing highly complex artificial coral reefs with geometries specifically designed to encourage biodiversity and give polyps a place to latch on.
They're also printing artificial muscles that mimic the reactive propulsion of squid for stealthy, non-disruptive underwater drones.
Right. Oh, and my favorite application is the seal whisker sensors.
Oh, yes. Faucet seals have these uniquely wavy whiskers that allow them to detect the hydrodynamic wakes left by swimming fish. By 3D printing sensors with that exact same wavy, undulating geometry, researchers created devices that can detect underwater flow disturbances over long distances.
With incredibly high signal-to-noise ratios, they even printed sensors mimicking the lateral line system of fish, allowing aquatic robots to detect subtle pressure changes in the water.
We are literally stealing R&D from millions of years of evolution.
We really are.
And this raises an important question for us. As we develop these manufacturing capabilities, are we simply forcing human architecture onto the ocean, or are we finally learning to print with the ocean's logic?
Right. So what does this all mean for you listening? We started this deep dive looking at how 3D printed microscopic cubic sponges can tame the violent turbulence of fluids. From there, we explored how chemical accelerators and dry laser cavities allow us to print concrete and solid titanium directly at the bottom of the sea.
We saw how this technology could completely rewrite military logistics on islands like Guam, assuming we can build the complex post-processing infrastructure.
And finally, we looked at Ocean Grid, turning the Gulf of Mexico into a graphene-oxide superfactory that solves water and energy crises, though not without posing physical risks to local marine life.
We are witnessing a profound shift. We are moving from manufacturing things for the ocean to manufacturing within the ocean. And I want to leave everyone with a final provocative concept that takes this even further.
Let's hear it.
4D printing.
3D printing. So, adding time as the fourth dimension.
That's the idea. In 4D printing, the object changes its shape, size, or function over time in response to environmental stimuli like temperature, moisture, or stress.
Oh, wow.
Researchers are currently developing untethered, stimuli-responsive soft materials, hydrogels, and elastic polymers that feature programmed, sequential self-folding.
Okay, imagine a future where these underwater 3D printed structures aren't just static blocks of material. What if the next generation of artificial reefs, or those massive graphene desalination lattices, are printed with hydrogels that dynamically adapt to ocean temperatures and changing currents?
They could self-fold to capture pollutants or change their porosity based on the tide.
They would effectively blur the line between a manufactured machine and a living biological organism.
Exactly. A machine that behaves and breathes like a living part of the ecosystem.
That is definitely something for you to chew on next time you look out at the ocean. Remember, that chaotic fluid environment isn't just an obstacle anymore. It's rapidly becoming our newest factory floor. Thank you so much for joining us on this deep dive, and we highly encourage you to keep exploring the sources for yourself.